In this video, we're going to talk about what filters are and how you can tell what a filter is based on a Bode plot. You may have heard of filters before. They are used quite often in many different applications out there. For example, the human ear can only hear sounds up to about 20 kilohertz, and so any sounds higher than that, basically we cannot hear. One thing they do is then they can filter out those higher frequencies in phone calls, and you won't even notice it because you couldn't hear the extra sounds there. And by filtering those out, they're able to have less information to send, which allows it to transmit your sound over through the cell phone to another person's cell phone much easier and with less problems by filtering that out. On the other hand, sometimes you want to filter out low frequencies that might cause like hum or other things going on in a given problem so that you can understand what's going on better. There are also times when you want to only hear a particular frequency. For example, if you're listening to a radio station that's only one frequency, you don't want to hear the radio stations at other frequencies. And lastly, sometimes you want to just ignore one frequency. Maybe someone is trying to interfere with what you're doing and they're playing a sound at one particular frequency and you don't want to hear that. You can then remove just that part of it while still getting all the rest of the sounds. These are the four types of filters we're going to talk about here. So the first is a low pass filter, and what your Bode plot would look like for a low pass filter is it would look something like this. So the idea is that for low frequencies, these are the low frequencies here, the output would be very high. If you want to just put things in numbers here, let's say this is, a 1 or 100% here. So that means, talking about transfer functions, it's output over the input. So for low frequencies here, we want the output to be equal to the input. We want to allow those frequencies through. And on the other hand, for high frequencies, we want to allow nothing through, zero output for that. So this would be a perfect low-pass filter that would only allow low frequencies through, and it would allow them through completely, and it would not allow any high frequencies through. Now this isn't very physically possible. The graphs don't have sharp corners like that. A more realistic one might look something like this here. So where you can, let low frequencies through the best, and then it will taper off so that it won't allow high frequencies very well. But usually there's going to be at least some sort of bleeding where some high frequencies will get through, but just not as well. It's going to be what's called attenuated, lowered. And then some lower frequencies, it might not let them through fully, right? Because it tapers off before the cutoff frequency there. But this is the main idea. So for a low pass filter, it starts out high and then goes low. The reverse for a high pass filter. So a high pass filter doesn't want to let any low frequencies through its zero. And then at some point in time, it's going to start letting all the higher frequencies through. And that's what the generic Bode plot of a high pass filter would look like. The third filter is a band pass filter. That's where you only want to let in certain range of frequencies. So it looks something like that, where it doesn't let in low frequencies, it doesn't let in high frequencies. It only lets in right in the middle, right at a certain frequency you decided on. Let's say you want to listen to a radio station and pick whatever number you want to. Let's say you want to listen to 99.9. Well, what that really is a range from 99.8 to 100.0. That is what this band would be. So your radio station would become a bandpass filter operating in just that middle region. And then as you turn your knob or you change your station on your radio, it would change where this is. So maybe you change your knob and suddenly you're only letting through this other frequency band for a different radio station. This is why at least if you've ever used an analog tuner radio where you would turn the knob specifically to get your radio stations, when you were kind of on the border between two different radio stations, you could hear both at least partially coming through. And that's because these bands, there's this little bit of overlap between one and the next. And if you're right in that region there, you're kind of letting both radio stations through, at least partly, and that's why you can hear them overlap. With the current digital radios, you don't hear this very often anymore, but this is just the idea of what a bandpass filter is. The last one, as I said earlier, is what if there's a sound at a certain frequency that's playing in your message, and you want to ignore just that one sound, but you still want to hear the rest of the message. This is a band reject filter where there's just one part that goes to 0, and the rest lets everything through on that. And so this is what the Bode plot would look like. So the point of this video is just to understand these 4 filters and what they mean in terms of their Bode plots and what's going on with them. We are going to see a couple examples of circuits that will give us filters like these, and we'll talk about those when we see them. But this is just a very brief introduction to filters because we don't have the time to do it more properly. However, if you go further in electrical engineering and communications, you will learn a lot more about filters and how to actually build them.